Hello, y'all. Welcome to another video. This is on like our last module. It's a smaller module. It's on conic sections and some of the last videos you're going to be watching for this course. So good on y'all for getting this far. So it's called conic sections. Why is it called conic sections? Um, well, if you look at a cone, right, this looks like a cone or like an upside down ice cream cone, right? And you took some sort of slice of this cone in any slice. Imagine I get like my knife and I slice this way, or I get my knife and I slice down, or I get my knife and I slice like horizontally. Well, what would the resulting shape look that you sliced out if I sliced down right here? The slice I would end up creating on the cone would end up being a parabola, right? If I took, this piece here, right, and just removed it from that area, on the cone, I would see like a parabola or an upside down parabola shape. Same if I sliced it horizontally here. If I sliced horizontally, I would get a hole in my cone, right? But the hole in my cone, by the way the cone is shaped, would just be an actual circle here. So there's circles, there's parabolas. And then lastly, you can slice diagonally. If I slice diagonally, then the resulting shape, when I look at my slice, will look more like we call them ellipse. It looks like an oval, but we call them ellipse in math land. So ellipse here. And that sort of visual is kind of like just fun just to know about, right? That why are we calling all these things conic sections, even though they have their own separate names? Well, you take a cone and you slice it a specific way, you're going to end up getting all the shapes we're going to be graphing in this section here. Um, so let's start with what we know. We've graphed parabolas in this class, right? We've sketched a graph of y equals x squared, right? You graph it just like so. Don't have to explain it that much because we talked about this a lot actually, but this is the graph y equals x squared. It's the parent graph. We talked about that before as well. And now we have a different form of graph. A key indicator that we're having a parabola is if there's a squared somewhere, and that's like the largest power, right? Like y equals x squared, y equals 3x squared plus 7x plus 1. I don't even have to graph it. I know because it's of this form, it's of a quadratic form, it's a parabola. It's going to be the same case when you switch these roles of x's and y's. Like what happens if you have x equals y squared instead of y equals x squared? Well, it's going to change the graph, of course. And we could even game this as like, I don't really know how to view things in terms of y squareds. I just know how to view things in terms of x's, right? So let's maybe solve for x. Let's start with x equals y squared and then square root both sides, right? We have, well, the square root for the y squares are going to cancel. We're just left with y. And then the square root for the x doesn't cancel. We just have square root of x. But remember, whenever we square root, we have plus or minus whenever you square root both sides like that. So what do we get as a result? We get y equals, let me do this up here, maybe. We get y equals a positive square root x and y equals a negative radical x here. And we've seen these graphs before as well, right? If you go to like a prior section in the radicals section, I know that y equals square root of x looks something like, let me go to blue again, something like this, right? That is the positive square root x function. Well, if I also graphed the negative square root x function, what does a negative do? Well, for parabolas, a negative will flip it to be upside down. The same thing happens for radicals as well. That's like the fact of adding an opposite, adding a negative to the equation. The fact is, our let's do this, let's color this red here. Our negative square root of x looks like this. And what do you know? This also ends up being a parabola, but now we're looking more sideways instead of up and down here, right? If this is my x and y axis, this is my x and y axis. This is where it ends up coming from. Fun fact, this is not a function. We're not going to be working with many functions here because functions are supposed to pass the horizontal line test, right? Horizontal line test, you can only pass the line once. Here we're passing the line twice, not a function. Either way, um, instead of doing this little rigmaroos here of, oh, I don't really know how this works, let's get to square root of both sides. Oh, I know how to graph square roots, and this is what I end up with. Instead of doing that, let's just recognize the fact again, when you have squares, of a single square, you get parabolas, like so, and whichever one is squared tells you which direction you're going to be opening. If it's y equals x squared, like before, we're opening up or down. If it's x equals and then a y squared, we open side to side here. So we're going to call this a sideways parabola. And whenever we see things with y squareds, we already know we're pushing towards a form like that, a graph like that. Okay, so when finding the graph of a parabola, we've already done it a lot in the quadratic section, but let's kind of like go and extend this further for y squared values. Well, how do we do it? We put the parabola in vertex form, right? You probably remember this formula, y equals x minus h squared plus k, where our vertex is h and k. Well, if you switch the roles of the x's and y's, it's going to have the same look. X equals a, y minus a. We also switch the roles of the k and the h because h is like your shift in the x direction, k is always your shift in the y direction. So when you're switching the x's and y's, you also switch the x's and k, or the h's and k's here. So in this situation as well, you have to like reverse what you already know, right? You have to reverse the roles that the numbers are in. But our vertex in this case is still going to be h and k. The number connected to your y is your y vertex value. The number outside is your x vertex value. So just always remember that how to do. Um, then you say which way the parabola opens. These are up and down ones. These are side to side ones, right? And then you find a vertex, which we already can find, and then find one more point closest to the vertex. We are not going to really need to do this part as much in the section because if you know which way it opens, you know where the vertex is, you know what the graph looks like, right? But on your ALEKS system for your homework, it will ask you to do that. So when we sketch your graphs, that's what we're going to do. Okay, let's graph using the above steps here. Well, notice for one, we have a y equals x squared and an x equals y squared. And actually, these look like the same exact equations. It's just that one of them's in the form of y equals x squared, the other one's in the form of x equals y squared and stuff, right? So the process for each of these should still be the same. And if you remember, how did we graph things like this? Well, one of the strategies we showed was putting it into this vertex form. And how do we put in the vertex form? We have to do some complete the square nonsense, right? And go from there. So that's what I'm going to do. We have y equals x squared minus 4x. And I'm going to add some space here, plus 9. Well, what do I need to add into here to complete the square? Using the complete the square nonsense will end up giving us a square value plus a number, which is exactly what vertex form looks like. So that's the idea here. Well, the complete the square value is b over 2 squared. Well, b in this case, negative 4 over 2. That is negative 2 squared or 4. So if I add 4 and then subtract 4 at the same time, I'm not adding anything new into the equation. That's the goal when we're doing algebra-based stuff. We don't want to change the equation. We want to massage, rearrange, manipulate so that things are of cleaner form for us. One way we can do this is by adding and subtracting the same number. It doesn't change the numbers. It's just because if I simplify this, it just becomes 0. But it's nice to have that 4 in here for completing the square. Because when we complete the square, we're going to have y equals x minus 2 squared from this part. And then this part just gives me negative 4 plus 9 or plus 5 here, like that. That's how I do it. Some people show it a little bit different work, so you can look at other videos for that. But either way, this is your H, this is your K. And because we have a positive here, not a negative number there, we know we have a vertex of 2 comma 5, and we open up. So I already can draw my graph. I go to here, I go over 2, 1, 2, 3, 4, 5. That's going to be my point here, and I already know I'm going to open up here. Now, because I have this extra thing I need to do, which is find one more point that's close to the vertex, I'll do that. But I say from my perspective, that would be enough to create the graph already. But this just adds a little more accuracy into what your calculator or your homework system is going to want. So let's plot a point. We want to plot a point that is close to the vertex. Well, my x value is 2 for this vertex. Why not just choose an x value of 1 and see what that happens? X equals 1. So we can plug it into any of these versions of the equation. I'll just use my vertex form here. We have y equals 1 minus 2 squared plus 5. What is this? Negative 1 squared plus 5. That's 1 plus this is 6. So we have a point 1 comma 6. Well, this is 1, 2, 3, 4, 5. Now we go to a 6 point. 1 comma 6 is right here. Now I can create the parabola. I already knew the parabola was going to look like this, but having one more point increases the accuracy of like how wide the parabola is supposed to be. So I suppose it's a good idea to do this. Okay, well, we've done these problems in the quadratic section, so this shouldn't feel new. This problem should feel a little new, but again, we're doing the same process, right? We want to put it in vertex form. Vertex form has a thing that has something squared, like a y minus a value squared in this form. So we do the same thing. I'm going to write this as x equals y squared minus 4y plus, oopsies, let's add some space, plus 9. What's the space I had in order to complete this square? Well, again, I'm going to show the work just because, I'm the professor and I show the work for the professor, but you should probably already see it's going to be the same thing as before. Negative 4 over 2 squared. Negative 2 squared is 4 here. So I want to add 4, subtract 4. And for this spot here, add 4, subtract 4. For this spot, that's a lot of 4s. For the the quadratic of these first 3 terms here, if you wanted to play the factor game, you could, right? It's going to be negative 2 and negative 2. That multiplies by 4. That's become negative 4. If you already see it, you don't have to do that factor game stuff. But this becomes y minus 2 squared plus 5, again, because this adds up to 5 here. Okay, again, we're at the stage. So what is my vertex? Be a little careful for what the vertex is, right? You might want to be like, oh yeah, it's negative 2 and 5 because that's just how it is always. But remember, your k is always connected to the y, and your x is always connected to your h, which is like your outside part in this kind of problem here. Remember, these h's and y's, or h's and k's, are switched when we have it of this form. So our vertex is going to be the inside is my y value, the outside is my x value. So here, vertex inside is my y value. So my y value is 2 for my vertex, and my outside is h. And also remember, this is a minus k. Whenever you have an inside part of your vertex, you need to switch the signs, right? Part of the rules we've had before. But okay, we do the same thing here. Oopsies, why do I keep moving this? There we go. Let's create my vertex like so. I want to go over 1, 2, 3, 4, 5 and up 1, 2. That's going to be my vertex point. And because this is positive, positive ones open right, negative ones open left. Because we're up x equals y squared, we know we're opening right or left. And because it's positive in the front, we're opening right here, like this. So I can draw that right away. I'm going to plot a point that also works for me here. So let's plot a point. So this is also interesting. Normally when you plot points, you plug in x values. In this case, I have it of a prime situation to plug in a y value in order to find an x value here. And again, this is of the switching of x's and y's mindset, so it should make sense to plug in a value for y instead. What's a value we can plug in for y? Well, what's a clean value? Y equals, oh, close to y equals 2 as well. Let's do y equals 3. Why not? Y equals 3. So x is equal to 3 minus 2 squared plus 5. This is 1 squared, or 1 plus 5, which is 6. So we have the point 6 comma 3 here. So let's go up 3, 1, 2, 3, like this, and over 6. So it should be this point right here. And since I'm opening right, I know I'm opening back. That's all you need to in order to get as much of accuracy as you want for these problems, especially with the Alex system. The Alex system just needs 2 points of a parabola and it does the rest, right? So that's very nice. Okay, we'll do again. I'll say remember those are the two forms we want. I shouldn't have done minus signs. I should have done just dots like this, but that's totally fine. So let's do that for these two problems as well when they don't look as friendly in the situation. Oftentimes you'll have graphs that looks like this or equations that look like this where everything's equal to 0, right? And we got to manipulate it to get it back to of these forms here, right? So let's do that. Um, well, in this problem, I see we have y squareds and we just have a single x on its own. So we're not going to be of this situation where you set y equal to everything else. It's going to be more of this situation where you set x equal to everything else. Then it's of the form we like, and then we can continue as we did in that prior problem here. So what I'm going to do in this problem is I'm just going to add x to both sides. This cancels. What does that give us? Well, that gives us x equals y squared plus 2y plus 6. But again, I'm looking ahead here. I'm going to add some extra room to this problem, right? And what's the extra room I want to add? Well, you do 2 over 1 squared. That's 1 squared over 1. So I'm going to add 1 and subtract 1 so I can do that complete the squared process. You didn't even have to do this if you can see it, right? It's like, oh, this is a classic thing that we always factor, and then that's going to be what's next. What does this leave us with? It leaves us with y plus 1 squared plus 5. This factored part goes exactly to this, and then this is the remainder added amount on the side there. Okay. So what is our vertex? Our vertex is, ooh, we gotta be careful here. The h value is 5, and the k value is -1. Your inside number is your y value, or your inside number is related to the corresponding variable it's a part of, and you have to switch the signs as well in order to get to that vertex form, right? We have x equals y minus k, so this is a plus, we have to think of it like a minus negative in this case. And then our vertex horizontal value is on the outside. And which way do we open? We open right here, which is also the work I would have put on this, right? We open right. This point already told me, but because this is a positive squared value or square term here, we already knew we were opening right. So opens right. And now we graph like so. We're opening right, right. Hopefully I am recording. Yeah, it looks like I'm recording. We're opening right. So if I go 1, 2, 3, 4, 5, -1, that is 1 point. Let's plot the point. Why not y equals 0? Plot y equals 0. So x is equal to 0 plus 1 squared plus 5. What, 1 squared plus 5 or 6? Keep having a answer of 6 here, so that's kind of interesting. Don't expect for that. So 0 comma 6 is my other point. I already knew it was opening right here, so that's what my graph's going to be. Maybe that looks a little more V. Let's make that look a little better. Let's make that look like that. There we go. So not too bad to graph those things. We'll do one more. This is probably one of the toughest ones of this video so far, though I don't think this section is that bad. The tough part just comes from the fact that we have a number in front of our y squared. It's going to be a horizontal parabola because we have y squared, so we should add this x to the other side. And I'm going to put x on the left side just because I like having it of this form. 2y squared plus 20y. I'm going to leave some space. We're going to need to do another step here. If you remember, yeah. I think I wanted this to be a minus 48 too. So let me just change this part of the problem to be a minus instead, which means this is also going to be a minus here. Because I think if I do it as a plus, then my number is just too big from what I was wanting. So a little bit of typo there. I apologize for that. Okay. If you remember, how do we complete the square of a section like this? The way we do it is first we want to factor the number, this front number, out of the first two terms here. So that's what I'm going to do. 2y squared plus 10y. You remember, if I distribute this back in, 2 times y squared, 2y squared, 2 times 10y, 20y. So I'm just undistributing that 2, if that's the idea. I'm going to leave some space plus 48 here. So now we do the game of trying to complete the square here. Oh, wait. Did I mess this up? No, let me look. I wanted this to be, no, I wanted this to be a plus. What was I thinking? Okay. I'm sorry, everyone. I'm sorry. Okay. I think we're good now. All right. We have a graph that looks like this. X equals 2, y squared plus 10y. So now what do? We want to complete the square. That's where I'm at. So completing the square, I take this middle value, right? Or the new middle value, I divide it by 2 and I square it. What is that going to be? 5 squared, 25. So I want to add 25 here, and that'll end up giving me a perfect square. So what do I need to do to offset what I want to add, right? I added 25 here. What do I need to do here? You guessed it. I need to subtract 50. 50. Ah, yes, it is 50 because when I distribute this back in, I didn't really add 25 to my equation. I added 2 times 25. I added 50 to the equation. So if I include 50 and I don't want to change things, I also have to subtract 50 at the same time in order to balance the equation like that. All right, x equals 2. Well, this will factor to y plus 5 squared. And then I have negative 15 minus plus 48 on the outside, which is minus 2. So what is my vertex? Vertex is negative 2, negative 5, right? This is my h. This is my k here, right? Remember, you're switching those roles when you have it as x's and y's are switched. And which way am I opening here? Open right. That is why I wanted to switch all these negatives here. I wanted to do that to open it left. So I'll show that in a second, but we'll just leave it like this for now. Like so. So I'm gonna go over negative 2, down 1, 2, 3, 4, 5, right there. And now I can plot a point. And let's plot, well, I'm plotting here. It's good to plug in a y value. So let's plug in y equals, we already have y equals negative 5. Let's do y equals negative 4. Right? I want to plug something that is close to my vertex, right? So I don't have like a weird, if I plug in y equals 0, then I'm going to have like 25 here. I don't want to graph like 25. I want to graph a small number. So I have what? X equals 2 times negative 4 plus 5 squared minus 2. That is 2 times 1 squared minus 2. That's 2 minus 2. That's 0, right? Is that 0? 2 times. Yeah, yeah, that looks good. So we have a -5 or -4 and 0, which is right here, right? Our value is 0, comma, -4. There we go. So our graph opens up and it's going to look something like that here. Okay, now what if this was negative, right? If I had a -2y, 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 -2y here, and I was the same form, then it would be opening left here, and it would look something like that. So I would leave it to you guys to graph that way. I wish I had an example of the other way as well, but this is just what we have. So let's just leave it like that. Okay, here. Let us see what we got. Let's have this be the star problem. Star problem. Write the steps kind of like we normally do, and that will be your points for watching this video. There you go. Thank you for watching.